Welcome to this session where we will begin to systematically review the ECG. We will look at the systematic approach you should take when analysing the ECG. Remember that in the exam, if you are faced with a life-threatening arrhythmia, then you must correctly recognise this. We looked in the last session at the basic ECG complex, the P wave being atrial depolarisation, the QRS complex being ventricular depolarisation. Let's be clear about what constitutes a Q, an R and an S. The Q wave is the first downward deflection following the P wave. Not all complexes will have Q waves, and sometimes they're very small. The R wave is the first positive or upwards deflection following a P wave. As I said, there may not always be a Q wave, and you may simply go straight from a P wave to an R wave. The S wave is any downward deflection or negative deflection following an R wave. The T wave is the wave that follows the QRS and is ventricular repolarization. On the right of this slide, you will see some figures that we consider to be normal. We will talk through the components of the ECG during this session. Now, for the purpose of this module, we are using the figures from Garcia 2015 edition as the reference range. Different publications will vary slightly. However, in your analysis and particularly your exam, you should use these figures as your reference ranges. What I'd like you to do first is pause the presentation and have a go on a piece of paper with this activity. From memory, will you draw a normal ECG complex? I would like you to label the P, the Q, the R, the S and the T. Label the PR interval, the QT interval and the ST segment. And try to recall the duration of the P wave, the PR interval, the QRS complex and the QT interval using the figures we've just highlighted from Garcia. Hopefully you have a piece of paper now which is similar to this slide. This is the system we would like you to use to approach the assessment of the ECG and to use in practice. The following slides will break down the sections further. Case studies will help you revise for the exam and will incorporate this approach. What I'll do is I'll release case studies in the coming weeks once you're a bit more familiar with this approach. From previous modules, the people who engaged in the case studies found that they're more prepared for the exam. There are a number of places on the Blackboard site where you can find this rhythm analysis sheet. It's in the formative assessment folder and is also in the learning materials folder. Start your analysis by looking at the ECG setup. Poor quality ECGs should be repeated. If you only have a rhythm strip, then you may wish to ask for a 12-lead ECG. ST segment anomalies may not be global, and axis calculation requires 6 limb leads to be seen. Look for calibration markers, as we've previously discussed. Check that the gain is set at 10 mm per millivolt, and that the paper speed is at 25 mm a second. Is the ECG adequate quality? In some situations, patient factors will mean that a perfect quality ECG is not possible. If you cannot interpret correctly an ECG due to quality, then consider asking for a repeat. Is there electrical activity? Now this seems rather obvious, however the Resus UK 2015 guidelines suggest that we start with this, and clinical situations will dictate the urgency of this assessment. If you're not familiar with the Resus guidelines, then take time to have a look. There's a hyperlink available, or go to the Resus Council UK website. If you're presented with a life-threatening arrhythmia, then you must acknowledge this and act quickly. In a life-threatening arrhythmia, you should follow an A to E, an airway to exposure assessment. Again, if you're not familiar with this approach, then go to the Learning Materials folder for this section, and there's a good article by Phil Jevon giving an overview of the A to E approach. Next, we are going to look at the components of the ECG complex. In your ECG analysis, say what you see. Sometimes descriptive words are appropriate, rather than trying to write a technical word. When writing commentary, and particularly taking measurements, state which lead you are referring to. How can we determine the heart rate? Now, in most ECG printouts, the machine will calculate a rate, but we need to be in the habit of calculating this ourselves. Once we've learned some of these techniques, it only takes a few seconds to work out. We looked at the ECG paper previously. On the standard ECG setup, the speed is 25 mm per second. Each large square is 5 by 5 mm and in time is 0.2 seconds. Each small square is 1 by 1 mm and in time that is 0.04 seconds. There are a number of different methods, all based upon the knowledge we have of standard ECG speed. In this method, we are going to use the large squares to calculate rate. This will work on a regular rhythm. Identify the R wave of a complex and then find the next R wave. Count the number of squares between the two R waves. In this case, we have 4 large squares. The calculation we use is 300 divided by the number of large squares. So 300 divided by 4, which is 75. In this ECG, the ventricular rate, because we're measuring QRS complexes, is 75 beats per minute. To calculate the atrial rate, we would use exactly the same technique, but take our measurements using the P waves. For a full ECG analysis, and particularly in your exam, you'll be expected to calculate the atrial rate and the ventricular rate of each ECG. A more accurate method to calculate rate is to use the smaller 1 mm squares on the ECG paper. Begin with the same measurement points. In this case, we're using the R wave, so calculating ventricular rate. Now count the number of small squares. I've counted 21.5 small squares here. The calculation we use is 1500 divided by the number of small squares. So 1500 divided by 21.5 would give a rate of 70 beats per minute. You will see this ready reckoner system in some of the books. It's great for a quick, rough guide, but it's not accurate enough for this module and certainly should not be used when making formal assessments of the ECG. In an irregular rhythm, the previous methods are not suitable. Start by identifying a measurement point on your ECG and count 6 seconds of time on the ECG, which is 30 large squares. Now count the number of complete complexes in this period. In this example, I am counting 11. I did not count the first complex as it is not a complete complex. Now simply multiply the number of complexes by 10. So in this example, 11 complexes multiplied by 10 will give us a rate of 110 beats per minute. How do we work out the regularity of the heart rate? This slide demonstrates how to use paper and marks to check on regularity. Take a piece of paper and mark a few points corresponding with the ECG complex. Use the same point on each complex. Now move the paper. In a regular rhythm, wherever you place the paper, the lines will mark up. Let's repeat this process with an irregular rhythm. We place the markers as before, but because this is an irregular rhythm, we'll find that the markers do not line up. When we're describing regularity of a rhythm, there are 3 descriptive words which we may choose to use. Regular implies that The rhythm is predictable and follows a regular pattern. When we use the markers on our piece of paper, no matter where we place them markers on our rhythm strip, we will be able to match up to the same points on the complex. When we're considering irregular rhythms, the example we saw on the previous slide was an irregularly irregular rhythm. What this means is there is no predictable pattern to the ECG. No matter where we were placing our marker, we were unable to line up our marks with the corresponding parts of the ECG complex. The example here being atrial fibrillation. A rather confusing name of regularly irregular is a rhythm which does have a predictable pattern but is irregular. We can see from the example here that depending on where we place our markers, we may be able to match up the complexes or we may not, but because there is a predictable pattern, we can see this emerging. So far, we have looked for electrical activity. We have checked the ECG setup, we have assessed the rhythm and the rate. Now let's start looking at the components of the ECG complex. The P wave represents depolarization of the atria. Therefore, this should be the first wave of an ECG complex. Sometimes we have to look very carefully for P waves as they can be discrete or even hidden amongst other complexes. The appearance of the P wave should be commented on, and we should be looking at the morphology of the P wave. The P wave should be rounded and 0.08 to 0.12 seconds in duration. The P wave is a small wave and should be less than 3 millimeters or 3 small squares high on the ECG. Atrial consistency is calculated by looking at PP regularity. Using the approach we previously discussed to assess regularity, measure out the P waves, and wherever we move markers along the rhythm strip, we should be able to predict where P waves are occurring. Preceding every QRS complex, there should be a P wave, and following every P wave, there should be a QRS complex. Chapter 9 of Garcia 2015 is a very worthy read in relation to P wave assessment, and particularly have a look at the section on abnormal P waves. When we're thinking about the PR interval, it is first of all important to clarify what we mean by the PR interval and where it is measured from and to. The beginning of the PR interval is at the beginning of the P wave. The PR interval is measured to the beginning of the QRS complex and not to the R wave. For this reason, you may sometimes read about a PQ interval, which is the same. The PR interval needs to be looked at in each complex in the rhythm strip. It may change from complex to complex. We will look at this in more detail when we look at heart blocks in a later session. A normal PR interval is 0.11 to 0.2 seconds. The QRS complex represents ventricular depolarization. First check for its presence. In every P wave, there should be a following QRS complex. The complex should be narrow, less than 0.11 seconds, and this is measured from the beginning of the Q wave to the end of the S wave. The point where the S wave ends and the ST segment begins is called the J point. The ST segment begins at the end of the S wave, which we call the J point, and ends at the beginning of the T wave. The J point is not always clear, so identifying the ST segment accurately can sometimes be difficult. We will look at the ST segment in much more detail in the ischemia and infarction session later in the module. For now, we should look if the ST segment is depressed or elevated. The ST segment should be electrically neutral. If we drew a line through the ECG between positive and negative waveforms, we would call this line the isoelectric line or the neutral line. The ST segment should be on this line. Example 1 shows an ST segment that is neutral. Example 2 shows an ST segment that is depressed to the isoelectric line. Example 3 shows an ST segment that is elevated to the isoelectric line. Depending which lead we are looking at will determine if we consider this ST elevation to be significant. 1 mm in a limb lead or 2 mm in a chest or precordial lead is deemed significant. The T wave is a representation of ventricular repolarization. It is either positive or negative. The T wave should be in the same direction as the QRS. If the QRS is mostly positive, then the T wave should be positive. If the QRS is mostly negative, then the T wave should be negative. The T wave should be asymmetrical with a slow upstroke and a fast downstroke. Take time to read chapter 14 of Garcia 2015 for a review of T waves. The QT interval is from the beginning of the QRS complex to the end of the T wave. It represents the whole of ventricular systole. There are a number of reasons why the interval can be varied. In most cases, this is due to heart rate, and other factors which can influence this are gender and age. The interval can also be changed due to electrolyte disturbance and some medications. When considering the QT interval, we have to be mindful of the influence of heart rate. If the heart rate is not 60 beats per minute, then the QT measurement should be corrected. Bazit's calculation is the commonly used technique. In the learning materials there's a very good article about QT calculation. Have a read of that and how Bazit's calculation is used in practice. The final part of our analysis is the calculation of axis. I touched on this in the previous session, saying we'll spend a good period of time looking at this later. We will be calculating axis from the limb leads, and remember we said that normal axis is between -30 and +90 degrees. Okay, let's have a look at some ECGs. I'd like you to pause the presentation now and, using the rhythm strip in front of you from lead 2, calculate the rate of this ECG. We discussed a number of ways to calculate rate. Hopefully you checked first that this was a regular rhythm, which it is. I calculated the rate at 75 beats per minute. There are 4 large squares or 20 small squares between the R waves, so 30 divided by 5 is 75, as does 1500 divided by 20. This is an example of sinus rhythm. The sine away chill node is firing at 60 to 100 beats per minute. When we're describing a rhythm as sinus rhythm, it must contain a number of features. There should be regular P waves, so we should be making an assessment of the P waves and making sure that the PP interval is equal and the PR interval is equal. The P wave should be upright in lead 1 and lead 2. Remember, we are measuring electrical activity coming towards lead 1 and lead 2, and therefore we know that any impulse that is travelling towards leads should be upright. P wave should always be upright in these leads because it's travelling from the SA node. There should be a regular QRS complex at 60 to 100 beats per minute, and this should correspond with each P wave. Every P wave, as we said, should be followed by a QRS, and every QRS should be preceded by a P wave. The PR interval should be constant and less than 0.2 seconds or 5 small squares. For a rhythm to be called a sinus rhythm, it must contain all of these components. Sinus bradycardia has these 2 features. a heart rate which is less than 60 beats per minute, and every P wave is followed by a QRS. What I'd like you to do is calculate the heart rate here. I want you to use two techniques, the technique counting the small squares and dividing into 1500, and the technique counting the large squares and dividing into 300. You'll want to pause the presentation now and please restart when you're ready. Hopefully you managed both techniques. The large square technique was around 5 squares, or slightly over, so calculating a rate of 60 beats per minute. The small square calculation, I counted 28 squares, so this works out at a rate of 53 beats per minute. And this is a good example of why you need to be careful when counting using these two techniques, as they can give different results. Which one would you use? Well, I would always choose the small square measurement over the large square measurement due to the improved accuracy of this technique. So when we're describing a rhythm as a sinus bradycardia, it must be a sinus rhythm display all the features of a sinus rhythm, which we discussed previously. However, the heart rate will be less than 60. It is unusual for sinus bradycardia to be below 40 beats per minute, and if we see this, then we should be considering heart blocks and medication side effects. Sinus bradycardia can be a normal variant, particularly amongst healthy and athletic individuals. Let's repeat the measurement exercise with the sinus tachycardia. What I'd like you to do is measure the rate of this rhythm. Again, pause the presentation and continue when you are ready. Again, depending on the technique you used will determine the answer you have. If you use the large square technique, then you'll have worked this out at around 150 beats per minute, with just over 2 large squares between each R interval. If you use the small square technique, then I counted about 12 small squares between each R wave, and this is 125 beats per minute. For a fast rhythm, I would always be wanting to use small square technique. So sinus tachycardia will also display all of the features of the sinus rhythm and will have a heart rate of over 100 beats per minute. It can be normal, particularly in an unfit individual, or an abnormal variant, or a response to a physiological insult or pressure. What I'd like you to do now is calculate the rate of this ECG. I would like you to tell me what is the rate at point A and what is the rate at point B. I want you to give me the exact heart rate, so use the small square technique and divide into 1500. For easier reading, I've zoomed in on section A and section B for you. You should pause now to do your calculation. Here, there is a slight difference in rate at the two locations. At point A, there are 19 small squares, so a rate of 69 beats per minute. At point B, there are 21 small squares, so a rate of 71 beats per minute. What we are seeing here is sinus arrhythmia. This is where there is a variation in heart rate during inspiration and expiration. There are a number of features that you must identify for us to say a rhythm is a sinus arrhythmia. Many of these features are similar to sinus rhythm, in that every P wave is followed by a QRS and every QRS is preceded by a P wave. We would describe this as a regularly irregular rhythm. It is uncommon after the age of 40 and very common in young adults and children. We should see that if we are monitoring this patient, the heart rate will vary with inspiration and expiration. Expiration will decrease the heart rate, inspiration will increase the heart rate. That is the end of this session. Remember to have a look at the learning materials to support the session. This week I'm afraid has been very heavy with materials, but I really want you to get these foundation layers built so you can make progress with some more advanced ECG analysis. Well done on getting through all the material, and I promise that next week will not be so heavy.